To connect the 3-bit decrementing counter on the trainer board using D flip-flops, we'll need 3 flip-flops. We can call them flip-flop 0, flip-flop 1, flip-flop 2. And for this we'll also need 3 output pins, so we can choose 3 of the LEDs and call them output 0, output 1, output 2. Output 0 being the least significant bit. Before we start the connection, we'll first connect the clocks of all the flip-flops together that we're using. And then the first connection we'll do is the clock signal. So we'll take the clock from the trainer board and connect it to one of the pins of the clock. So either this pin or this one or that one. Next, we'll connect D2. D2 requires the use of a 3-input OR gate. The first input takes Q2 bar, Q1 bar, Q0 bar, AND together. The second input takes Q2 and Q0, and finally Q2 and Q1. So let's first take Q0 bar, Q1 bar, Q2 bar, and AND them together in this 4-input AND gate. So we'll connect first Q0 bar, which is the second output of Q0. Then we'll take Q1 bar, which is the second output of Q1. And then Q2 bar, which is again the second output of flip-flop 2. The extra input of this 4-input AND gate that is not used will be connected to 1, because 1 and A is equal to A. So 1 here will not make a difference. Now we'll connect the second AND gate. We'll choose one of the 2-input AND gates and we'll connect the pins to Q0 and Q2. So the top wire will be Q2, and then this pin will be connected to Q0, which is this pin right here. Lastly, for D2, we need another 2-input AND gates, another 2-input AND gate that takes Q2 with Q1. So I'll take a copy of Q2, can take this a wire from this pin, just to make it cleaner. And the second input of this AND gate should be Q1. So we'll connect this pin to Q1, which is this pin right here. It is Q of flip-flop 1. Now, the outputs of these 3 AND gates will be ORed together in a 4-input OR gate. So let's connect the output of the first AND gate, and then the output of the second AND gate, and then this 4 AND gate to the 4-input OR gate. The additional input of this OR gate that is not used will be connected to 0, because again, A or 0 is equal to A. So 0 for the OR gate will not make a difference. 0 is the black bar here, any of the pins will suffice. Now the output of this OR gate is actually D2. So we'll take a wire from here, connect it to D of flip-flop 2, which is this pin right here. Now D2 is complete. We're gonna connect now D1. D1 is equal to Q1 bar and Q0 bar, or Q1 and Q0, which can be expressed as Q1 XNOR Q0. So we need an XOR gate and a NOT gate to implement D1, just to make it simpler. So we'll take a wire from Q1 and a wire from Q0 and connect it to the XOR gate, one of the XOR gates that we have. So let's take first Q1. Q1 is actually this pink wire. Q0 is this red wire. So we can take them both and XOR them together, the pink and the red. This is the output of the XOR gate, but we want XOR bar, which is XNOR, so we'll need to connect the output of this XOR gate to a NOT gate or an inverter, like such. And then the output of this inverter is going to be our D1. So we'll take a wire from the output of the NOT gate and connect it as D1, which is this pin right here. For D0, we need to simply connect it to Q0 bar. Q0 bar is the second output of flip-flop 0, which is this pin right here. We take a wire from Q0 bar and connect it as D0. Now the connection is complete except it's missing the connection of the output, and we said output 0 is equal to Q0, so it's this red wire. Output 1 is equal to Q1, which is this pink wire. And finally, output 2 is equal to Q2, which is the output of flip-flop 2, the first output of flip-flop 2, which is this green signal. After completing the connection, we have to test it. So before we test the combinations that we'll receive at the outputs, we'll first make sure that the clock speed is comfortable. We can move the knob slightly to the left or to the right to make sure it has a comfortable speed that allows us to observe the outputs. And for a 3-bit decrementing counter, we're expecting the counter to count from 7 to 0. So 7, 6, 5, and so on until it reaches 0, and then it will reset back to 7. Keeping in mind that output 0 is the least significant bit. So that means if this LED is on, it means the current count is 1. If output 2 is 1 and everything else is 0, then the current count would be 4. Okay, so this is the complete connection of the 3-bit decrementing counter on the trainer board.